Hello student, I am Dr. S.L. Munde, Assistant Professor Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in previous lecture we have seen pure birth process model. Then also we have seen pure death process model. Okay, so in this lecture we will see Poisson distribution classification of the queuing system. That means the some model of the Poisson distribution. Okay, so in this lecture we will see the classification of the queuing models. Dear student, generally the queuing models may be completely specified in the following symbolic form. Okay, so this is the symbolic form of the queuing models. In bracket A oblique B oblique C double dot D oblique E. The meaning of this A, B, C, D and E as follows. Okay, the first and second symbols denotes the type of distribution of inter-arrival times. Okay, so this is first A and B. So this symbol denotes the types of the distribution of inter-arrival times of the inter-service time respectively. Okay, third symbol is denoted as the number of servers. Third symbol is denoted as the number of servers, that is C is denoted as the number of servers. And fourth, D number 4, the fourth symbol is denoted as the capacity of the system, and letter number E, that is 5 numbers, which denote as the Q discipline, which is denote as a Q discipline. Okay, so these are the some meaning of the A of the above letters. Okay, generally the models is denoted by the following letters. Okay, so following letters is can be used in the queuing models. So capital M means Poisson arrival or departure distribution. Capital M means Poisson arrival or departure distribution. EK, Erlangian or gamma inter arrival for service time distribution. So these are the some letters related to the queuing models. GI, general input distribution, and G is general service time distribution. Okay, and finally capital M oblique EK oblique 1 double dot infinity oblique FI F0, which defines a queuing system in which arrival follows Poisson distribution. Service time are Erlangian. Single server, one means that is single server. Infinite capacity, first in first out. F0 means first in first out. So this is a Q discipline. Okay, so this is the meaning of this distribution, meaning of this model. Okay, so M means Poisson distribution, EK means service times are Erlangian, one means single server, infinity means infinite capacity, F0 means first in first out, which is a Q discipline. Okay, so this is the meaning of the models. Now in a queuing system, in queuing model, the transistant and steady state are the very most important most important uh, we can say that equations, transition equation or steady state equation. Okay, so a queuing system is said to be a transit state when it operating characteristic like input, output, mean queue length, etc. are dependent upon time. If the characteristic of the queuing system becomes independent of the time, then the steady state condition is said to prevail. Okay, so this is the uh, uh, steady state equation. Okay, so here Pn of t is the probability that there are n customers in a system at the time t. Okay, then the steady state equation can be defined as limit t tends to infinity, Pn of t equal to Pn, so independent of t. Okay, so this is the transient and steady state equations. Now we will see the Poisson queuing system. What is the Poisson queuing system? Queue that follows the Poisson arrival exponential inter-arrival time and Poisson services exponential services time are called as Poisson queue. So in this section we will study some queuing system model. Okay. So in this Poisson distribution, so this is the Poisson distribution. So in Poisson distribution we will study some Poisson queuing system model. Okay. So first model is M1 infinite Fi F0. Okay. So this is the first model MM1 infinite Fi F0. So this model which deals with the queuing system having a single service channel. Poisson input, M means Poisson input, exponential service, and there is no limit on the system capacity, that is infinite, while the customer are served on a first in first out basis. Okay, so this is the meaning of this MM1 infinity FIF0 model. Okay, now we will find out the steady state differential equation of this model. So in step number 1 we will construct the differential difference equation. So let us suppose that Pn of t be the probability that there are n customers in a system at a time t. The probability that the system has n customers at a time t plus delta t. Some customers will arrival at a different time, that means t plus delta t, can be expressed as the sum of the joint probabilities of the 4 mutually exclusive and collectively exhaustive events as follows. Okay, so some customers will come in time to time in different time. Okay, the probability of that persons can be written in the following form: Pn t plus delta t. So t plus delta t means different time, or we can say the increment in time. Okay. So Pn of t into probability of no arrival in delta t. What is the first probability? Pn of t, no arrival in time delta t, probability of no arrival in time delta t, into probability of no service completion in delta t, plus Pn of t, probability of one arrival in delta t, into probability of one service completed in delta t. Okay, if no one will in delta t, then no service will completed in delta t. Probability of no will come in delta t time, and that time no service will complete in that delta t time. Second will be if one arrival in time delta t, then only one service completed in time at delta t. Then plus Pn plus 1 of t, no arrival in delta t, that means no will arrive in delta t, then one service completed in delta t. Okay, because that time one service is completed in delta t. Then probability of n minus 1 of t, p, one arrival in delta t, no service completion in delta t. Okay, so these are the some probabilities of the queuing system. Okay, now we will this obey the uh, above MM1 infinity FIF0 model. Okay, so this is the probability of the above MM1 infinity FIF0 model. So this is the this is the word type of the data. Okay, now we will write in mathematical form of this data. So this can be written in mathematical form: P n t plus delta t equal to Pn of t. Okay, 1 minus lambda delta t plus order of delta t, that means no arrival in time delta t, into 1 minus mu delta t plus order of delta t. Okay, plus Pn of t lambda t mu delta t plus P n plus 1 of t. Okay, so this is the mathematical form of this term. Okay, so this can be written as in Pn t plus delta t minus Pn of t. So if you take Pn of t transfer to left hand side, we will get minus lambda plus mu delta t Pn of t plus lambda delta t Pn plus 1 of t plus lambda delta t Pn minus 1 of t plus order of delta t. So after rearranging the terms and some uh, cancelling some terms, okay, and transferring to left hand side, after that we will get this equation, okay. So if you observe here, delta t is a very small, very small, okay. That delta t means the change in time. So here the delta t is very small. So in the terms involving delta t bracket square, delta t bracket square can be neglected, okay. So from this, where is a delta t square, that term will be neglected. Dividing the above equations by the delta t on the both side, then the taking limit at delta t tends to 0, we will get. So this equation we will divide by delta t, then we will take the limit delta t tends to 0, okay. So after taking limit, we will get dd of dt Pn of t equal to minus lambda plus mu Pn of t plus mu Pn plus 1 of t. P means here probability, plus lambda Pn minus 1 of t for n greater than equal to 1. N means number of person in a queue, okay. So number of person always greater than equal to 1. So similarly, if there is no customer in a queuing system, in a system at a time t plus delta t, that means n equal to 0, there will be no service completion during the time delta t. That means thus for n equal to 0, n means number of person. So if there is no person, that means n equal to 0, okay, and t greater than equal to 0, t must be the greater than equal to 0, okay. T time always is increasing time. So we have only two probabilities instead of 4. Thus the resulting equation is P0 of t plus delta t equal to P0 of t in bracket 1 minus lambda delta t plus order of delta t plus P1 of t in bracket mu delta t plus order of delta t 1 minus lambda delta t plus order of delta t, okay. So after arranging and transferring P0 of t left hand side and some cancelling some term, okay, so we will get this term, that is P0 of t plus delta t minus P0 of t equal to minus lambda delta t P0 of t plus mu delta t P1 of t plus order of delta t, okay. Now we will divide on both side by delta t, then we will take the limit with limit, that is delta t tends to 0, okay. So after dividing on both side delta t and taking limit delta t tends to 0, we will get dd of dt P0 of t equal to minus lambda P0 of t plus mu P1 of t for n equal to 0, for n equal to 0. So here we have find out the equations for no service will completion in during the time delta t for n equal to 0, okay. Now we will derive the, so this is the difference equation. Now we will derive in step number 2, we will derive the steady state difference equation. So in steady state, Pn of t is independent of time t and lambda less than mu when t tends to infinity. Thus Pn of t tends to Pn, okay. So which implies dd of dt Pn of t tends to 0 as t tends to infinity. Consequently, the differential difference equation obtained in step number 1 can be reduced in the following form. Equation number 1. So this can be equation number 1. This can be reduced in the following form, that is minus lambda plus mu Pn plus mu Pn plus 1 plus lambda Pn minus 1 for n greater than equal to 1. Okay. So this equation, not this equation, this equation, okay. So this can be written as, that is 0 minus lambda, and this equation can be written as, that is 0 minus lambda Pn plus mu P1 for n equal to 0, okay. Similarly, consequently the difference equation obtained in step number 1 can be reduced 0, okay. I think this is a repeated step, okay. So so these are the repeated step here, okay, I think. So this is called as a steady state difference equations. Now step number 3, we will find out the solution of the steady state difference equation. Okay. For the solution of the above difference equation, there exist three methods, namely as the iterative method, use of generating function, and use of the some linear operators. So out of these, we will use which method? That is the iterative method. Okay, so by using iterative method, the difference equation can be obtained after solving p1 equal to lambda upon mu p0. Second, p2 equal to lambda plus mu upon mu p1 minus lambda mu p0. So we will get lambda by mu bracket square p0. P3 is, so after solving you will get P3 is lambda by mu bracket cube P0, and in general can be written as Pn equal to lambda by mu to the power n P0. So this is the general term. So for n plus 1, Pn plus 1 equal to lambda plus mu upon mu Pn. So you will get minus lambda by mu Pn minus 1 for n greater than equal to 1. Okay. Now we will put all the values P1, P2, Pn and Pn minus 1. We will get in a steady state difference equation, we will get Pn plus 1 of lambda plus mu upon mu lambda by mu to the power n P0 minus lambda by mu to the power n minus 1 P0. So we will get lambda by mu to the power n plus 1 P0. Okay. Thus the principle of mathematical induction method, the general formula for Pn is valid for n greater than equal to 0. Okay. Now here we will find out the value of P0 by using the boundary conditions, that is summation n equal to 0 to infinity Pn equal to 1. So which is equal to, we will put the value of Pn. So 1 equal to summation lambda by mu to the power n P0. Okay, so we will get P0 summation lambda by mu to the power n. Here Pn is lambda by mu to the power n P0. The value of Pn, the value of Pn from this equation we can put. Okay, so this can be written as, after solving, P0 equal to 1 minus lambda by mu. Here lambda by mu is less than 1. Okay, so therefore the steady state solution is given as Pn equal to lambda by mu to the power n 1 minus lambda by mu, and which is equal to rho to the power n 1 minus lambda, where here rho is lambda by mu and which is less than 1 for n greater than equal to 0. Okay, so this expression gives the probability distribution of the Q length. Okay, so this is the MM1 infinity Fi F0 queuing model, that is first model. Now we will see some characteristic of this model. So probability of Q size being greater than or equal to K, the number of the customers is given by, probability of n greater than or equal to K, which is equal to rho to the power n. Okay, so this is the calculations part. Okay, that is summation Pk. Okay, so these are the calculations part. Then the average of number of the customers in the system is given by, that is E of n equal to lambda upon mu minus lambda, or it can be written as rho by 1 minus lambda. Third, average Q length is given by. So these are the some formulas when you are going to solve the problem. So these formulas are very important. This formula is very help to solve the problems. So average Q length is given by E of m, that is equal to summation m Pn, where m is n minus 1. Okay. So E of being a number of customer in a queue excluding customers which is service. So E of m, so you will get, that is lambda square upon mu minus lambda. Okay. Number 4, average length of non-empty queue is given by. So it is denoted by E of m such that m greater than 0. So which is equal to mu upon mu minus lambda. Since here probability of m greater than 0, that is P of n greater than 1, and which is equal to summation Pn minus P0 minus P1. So we will get lambda by mu to the power 2. Number 5, the fluctuation of the Q length is given by, that is variance of n equal to summation n minus expected value of n square Pn. So which will be, that is summation n square Pn minus expected value of n bracket square. So by using the some algebraic transformation of the using the some algebraic transformation, the value of Pn can be reduced to be variance of Pn equal to lambda mu upon mu minus lambda brackets power 2. Okay. So these are the some characteristic of the model number 1. Now we will see the some problems on our model number 1. So what is the first problem? A TV repairman finds that the time spent on his jobs has an exponential distribution with a mean 30 minutes. If the repair sets in the order in which they come in, and if the arrival of the sets is approximately Poisson with an average rate of 10 per 8 hours day, what is the repairman expected idle time each day? How many jobs are ahead of the average set just brought in? Okay, so this is the example related to the TV repairman. Okay, so if you observe here, so here we have to find out the we have to collect the data. So in if you observe here, so here we have given, so here we have given average rate, that is it is denoted by lambda. It is average rate is 10 per day. So lambda is equal to 10 sets per day and mu is 16 sets per day, and mu is 16 per day. So therefore rho equal to lambda by mu. So 10 by 16, that is 0.625. Okay. So what is next? The probability for the repairman to be idle is, that is P01 minus rho. So which is equal to 0.375. Then we will find out the expected idle time per day. So therefore the expected idle time per day 8 into this P0, that is 0 into 375, that is 3 hours. Then expected average number of TV sets in the system, it is given as E of Pn rho upon 1 minus P, 1 minus rho by using formula. So after solving we will get, that is 2. The TV repairman sets the two TVs in a per day. Okay, so this is the first example. Second example, in a railway marshalling ad, goods train arrive at a rate of 30 trains per day, assuming that the inter-arrival time follows the exponential distribution, and the service time distribution is also exponential with an average 36 minutes. Calculate the following. The first, the mean queue size and the probability that the queue size exceeds 10. If the input of the train increases an average 33 per day, what will be the change in 1 and 2? Okay, so first we have to write down the what is the given data. Okay, so here average is given as, that is lambda equal to 30 divided by 60 into 24, that is 1 upon 48, and mu is 1 upon 36 train per minute. Okay, so therefore rho is lambda by mu, so which is equal to 0.75. Then find out first, that is Em rho upon 1 minus rho, so you will get 3 tens. And second is probability of greater than equal to 10, that is rho to the power 10, so which equal to 0.06. Okay, so what is the next? Third, if when the input increase 33 trains per day, what will be the change? So lambda equal to 33 instead of 30, 60 divided 16 to 24, so you will get 11 upon 480, and mu is 1 upon 36 10 per minutes. So here will be changed, that is rho equal to lambda by mu. So 11 upon 480 into 36 instead of 30, we will get 0.83. Then we will get first, that is the mean queue size E of n equal to rho upon 1 minus rho, that is 4.9, or which equal to 5 trains approximately. and second is probability greater than equal to 10, rho to the power 10, so which equal to 0.2 approximately. Okay, so this will be the change if the input trends increase to an average 33 per day. So these are the some examples on a model number 1 MM1 Infinity A5F0. So dear student, problem number 3 and problem number 4 I will give you for the purpose of homework. Okay, so you have to read problem number 3 and problem number 4 as a homework. So in next lecture we will see the next model of the of this unit.